Hello, and welcome back to another episode with ItsDrDan. And today we're going to learn all about electron configuration and to how to use the tools that you have around you during an exam so that way you are able to ace it. The one thing you're given on every test in any class is always a periodic table. So trying to memorize all these different methods on how to solve electron configuration can be exhausting and difficult. So let's learn how to use the resources that are available to you. Now, let's get into it and try to understand what is electron configuration. Well, one thing that you learned about back right before electron configuration was this idea of the Bohr model. But the problem with it, it's not enough. It does not talk about how electrons, how they repel each other. It doesn't describe exactly how these methods work. So why we need electron configuration, it's how we can exactly organize ourselves. Almost like the same way how you might organize your kitchen, for example. Cups go in a certain place, plates go somewhere, bowls go somewhere, food goes somewhere else. They all have their own set place. Electron configuration is the same way. So if I have this Bohr model up here for chlorine, well, we can do the exact same thing and put things into specific orbitals where they belong rather than these orbits. Orbitals are a three-dimensional picture for us to tell us exactly where they're going. Now, we can show this in a complete way or as well with noble gas configuration as well. So let's go into trying to understand exactly what this entails and what type of orbitals we will see. So there's different types of orbitals that you will see. They revolve around the following letters of S, E, D, and F, which are based on the shapes of the orbitals of how they are located around the nucleus of an atom. Now, each of these orbitals contain a different number of electrons. The first one, S, is one of our lowest levels. This one always has 2 electrons in its orbital and only has one orbital to have those 2 electrons. With P, we have 3 orbitals fitting 6 electrons in them. And one thing that you can see with that is, well, we have a trend where we can only fit a total of 2 electrons in every orbital. Now with D, what we're going to be seeing there is now we're at 5 orbitals. With those 5 orbitals, you can fit a total of 10 electrons in them. So what we always do is we fill in orbitals from left to right. We make sure everybody has their own room first, and then we fill in all the remaining electrons. Our last one is F orbitals. So with F, we have 7 orbitals that are available to us, and they can each fit 2 electrons. Now, with all these different shapes, what I'm going to be showing you next is examples of each individual orbital, but let's show how these are situated on our periodic table so that way we're able to use it, and that way you can use it along with these examples and try to solve them for yourself. Our periodic table looks a lot like this, and you might have a very similar one that maybe your teacher potentially handed out to you for your course. It doesn't matter exactly which one you have. All of them have different amounts of information on it. Usually when you're in a class, all you're given is the elemental symbol, the mass number, and the atomic number. But we can still use this just to show us how exactly we can organize it. So let's first try to switch it up so that way you can see it in a different light. With the periodic table, the first thing is you can kind of see there are very general features around it, certain shapes. Like for example, if you see around this top column, there's an area, there's this top column over here. There seems to be this area over here that's different, and also the area down here. So let's switch it up. Okay, change the picture up. So what this is we overlaid our periodic table with all the general shapes that you are going to be seeing on your periodic table. Our first 2 columns over here on the left, this is referred to as our S block. Notice how there are 2 columns here. So the shapes tell you how many electrons. If you remember, S had 2 electrons, and we can see we have 1, 2 columns there. With P, right, that had a total of 6 electrons. We can see 1, 2, 3, 4, 5, 6. The shape is in the table. So trying to remember like the diagonal method or all these other methods really can't help you if you don't remember them. So remember your shape. So other things with D block that could fit 10 electrons, right? So we can see that here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the last one was the F block. Well, F block down here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, right? We have all those individual pieces. Now, that's not the only thing though. It's not only shape. It's also based on energy level. How can we tell energy? Well, there's another helpful thing, right? We just counted a bunch of columns. What about the rows? So over here on the left-hand side of our periodic table, I've put all these individual numbers here as well. These are referred to as N levels, also known as your quantum level. The way to view it is like walking up flights of stairs in like maybe a really tall building. So you start at your first floor, you walk up to your second, your third, your fourth, your fifth, and the farther you have to walk up, the higher more energy you have to use to get there. It's very similar. The farther you are from the nucleus, the more energy. So we're going to be using that as well. Now, how can we actually be able to show all these individual levels of electron configuration? The way we're going to read this is like you're reading a book. You start from the top and you read from left to right, okay? And then you go down a line, you read from left to right, and we're going to continue across counting all of our orbitals. So we start at S, go all the way over to P, and so forth. So let's look at a bunch of examples here. And here I have all the orbitals listed in the exact order. So if it's something you want to write down for yourself, you can, right? It goes 1s, 2s, 3s, and so on. You can read all those there. You can pause it, take note of that. Let's go through some examples. Let's start with our s orbital example. Okay, so for our first example, we're going to look at lithium, which is an s, just looking at the s orbital configuration. So earlier I mentioned that we're going to be reading our periodic table like a book. So the first thing you want to do is figure out exactly where do you want to stop reading of your book. How many sentences do you want to read? Do you just want to read one chapter? You want to read it from cover to cover? Well, if it's like a science book, you just want to read the information you need. So here we're going to go right to lithium, which is right here. And what that tells you is that we need a total of, or we have a number of 3 on it, which we have a total of 3 electrons, 3 protons. So let's go through this. How exactly do we start? Well, we start from the top. Well, like I said, we read across our top row, and that is going to be on row number 1, right? So we can see that number 1 there that we saw earlier. Now, being that this is the s orbital, hydrogen and helium both have s orbitals. So we will do 1s2. Now, being that that's our first row, we're then going to go down to the second line of our book, ending at lithium over here. So that's going to be our 2s. Now, where do you stop? Well, we're stopping at the first column, right where lithium is. So this is going to be 1s2, 2s1. Now, that is just all you got to do for your complete configuration of lithium. It gets pretty simple at first. It gets more complicated the farther we get down. Now, one thing we can always do for ourselves, we can abbreviate these different structures. So a noble gas configuration is referring to the last column of our periodic table. I'm going to turn that red just so we can show it. So noble gases is everything that's on this column here, right? So everything that's down here. Now, one thing you'll notice is that, well, what noble gas is above it, above lithium, that is, and that is helium, right? If you look up one row up, you can see helium is right here. So what we can actually do is we can abbreviate our configuration, which stands for that 1s2 with helium, and then just put helium 2s1. Now, for now, it doesn't seem like it makes a lot of sense, but as we go further down, abbreviating is going to make a lot of sense later. Let's go on to a p orbital example. Okay, with our next example for a p orbital example, let's look at silicon. So with silicon, what we're going to be looking for is, let's find that on our periodic table, and we can see that it's right here. Now with this one has 14 electrons. Now with this example, we're going to make sure I specify exactly why we are saying that out loud, because there's a way for us to double check ourselves. So let's move some things over a little bit. So we are going to find the complete configuration of silicon. So once again, we're going to start the same way. We start at the top, and notice how I moved helium over here to help show that s orbital configuration. So that is our first level. That is going to be 1s2. We're going to go to our second line of our book. See lithium from last one, and then beryllium. That's going to fill in the next piece. So 1s2, 2s2. Now, in this case, we have to continue reading across the page, right? Even though there's all this stuff in the middle, we read all the way across the boron. So boron to neon. This is your 2p level, right? So it's still the second line, but it is now a P shape. So with this, it's going to be 2p6 because there's a total of 6 columns that we're reading, right? So boron was 1, carbon was 2, nitrogen 3, oxygen 4, fluorine 5, neon is 6. Now for the next one, we then come down to our next line, which is sodium magnesium, which is 3s1, 3s2, and then we'll go do aluminum and silicon. So what that will be is 3s2 followed by 3p2. Now, when it comes to this, what we now have to do is our noble gas abbreviation. But before we do that, let me show you a trick to make sure you ended in the right spot. So if you remember before I showed you that there was 14 electrons, well, there is a way for you to double check your work. So if you add up all of the exponents here, the superscripts, so we have 2, 2, 6, 2, and 2. So add those together. 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, and 12 plus 2 is 14. So if you add up all these numbers together, this makes a total of 14 electrons, which allows you to be able to see that we have that complete number of them. It's a check. You want to check yourself. Now, what else is there? Same thing as before. We're going to look for the noble gas that's above silicon here. If you look over, well, what's above it? Well, we can see neon is right above it right here. So neon is your choice of gas. So we will write that in as neon, right? And what that is going to be representing here is all the individual gases that are up on the second level. So I wrote this like this on purpose so that way you can see like, okay, all of these ones are neon's electrons, right? If you were to figure out the configuration for it, 1s2, 2s2, 2p6, that is neon. That has its 10 electrons. So now all we have to do is write 3s2, 3p6, and that would be your configuration. Let's do the d orbital example. Okay, with the d orbital example, this one is a longer problem. Same with the f orbital one. So with the d orbital, what we're going to be looking for is vanadium in this case. So with the V, so we can see vanadium is right over here. So this one has a number of 23 above it. So it has 23 electrons. So when you go through this, double check your math to make sure you're getting there. So same as last time, we start from the top and we're going to be reading from left to right as we're going through these. Now, the thing with the d orbital, there is a different trick when it comes to the n number or the total number of columns. So if you kind of remember that picture from before, so let's go back to that real quick. So to this picture, one thing that I forgot to mention before is that the D level and the F levels quantum numbers are different than before. Now, the quantum number was referring to the columns. So S is normal, P is normal. So they're just your normal n numbers. With D, what we actually do is we do n minus 1 for those levels. And then with F, we do n minus 2 for our levels. Let's go back to our example to show how that's going to be used. So like I was mentioning, we're going to be reading this like a book. So what we will do is we will start from top to bottom. So we'll start with the 1s2 area. So we will do that first. So hydrogen, helium. Then we'll go down to lithium, beryllium. So 1s2, s2. We'll go from boron to neon. Then we'll go to the next row, which is 3s2, then 3p6. Now, when we get to the fourth level, which is right here, so potassium and calcium, that's going to be 4s2. Now, like I mentioned, D is n minus 1. So what we are going to do is we have 1, 2, 3. So this is not going to be 4D, but it's going to be 3D3. And that is your electron configuration for vanadium. Now we can double check ourselves. We can add up all these individual values and we should get 23. So if we do 2 plus 2, that is 4. 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 6 is 18. 18 plus 2 is 20. 20 plus 3 is 23, right? We have our math. So how can we try to sum up all these individual values as a noble gas configuration, being that we have everything right? Remember all these top numbers here, these are all going to be our noble gas. And what we're going to do is find the noble gas that is one above it. And we can see that we have argon right here. So argon is our noble gas. And then we carry down everything else. Now, the cool thing about this is it helps it make it a lot easier. It's easier to write, it's quicker, but it all depends on your homework and your exams. So exactly what are you being asked? If it says complete or full configuration, write the full one out. If it's noble gas, save yourself the time and the energy and the anxiety. Let's do an f orbital example. Okay, with an f orbital example, this is a tougher problem. Exactly what do we have to do while going through this? We have to find neodymium, Nd. So let's try to find it. Now the f orbitals are always down here at the bottom of the periodic table. So it's like this extra little piece. Now, one thing, depending on which version of the periodic table you have, whether it's the new one or the old one, you might have counted here earlier. It wasn't exactly 14 columns on mine. There's 15 for mine. Every one of them's different. Check yours to see which one you have. Now, the reason is these two elements, they actually are right here. And usually you always have a piece that tells you like, hey, this is where you start counting them, which is right in here, which is where those f orbitals are going to start. So Nd is right at this spot. So let's go through the example so I can show you how to go about it. And what we're going to do is we're going to read our periodic table like normal, and we'll get down to the 6th level. So right here, 1, 2, 3, 4, 5, and then 6. And then I'll show you how to do the f orbital example. So with this, we kind of just show it like normal. So we start off from the top, right? It would be 1s2, then it would go down to 2, then it's 5, 4, 5. So let me write down all those individual numbers. So that way it'll help you see them on here. So this is going to be 1s, 1s, 2s, and so forth. So let me fill all these in so that way you can have them for yourself. So we can see how this is going to be changing. And you can really see how all those individual levels are different, especially when it comes to S, P, D, and then F as well. So that way we have all those individual levels. Okay, so let's fill in our numbers because pretty much we have complete orbitals from here on out. So we're going to do 5s is next. And then we will fill in the rest. So let's fast forward till I get to that little bit. Okay, now we are at 6s2. So 6s2, what we can see here is now we all of a sudden have the lanthanides, which is our F block. So our goal was to get to here. So what this will be is we'll have our 6s2, and then it's n minus 2, so it's going to be 4f. And then being that it goes to the 3rd spot, so keep in mind that these belong here. These are the D group on my periodic table. So we start at cerium, and then we go 1, 2, 3. So this is going to be 4f3 for our example. D orbitals are really freaking hard when you have to do them. Hopefully you don't have to do many. Usually it's a homework example. Very rarely do you see them on exams. So noble gas configuration, how do we go about it? Well, same as before, we end around the P group. So all of these are going to be, we're going to style all these to be red. So we can show all those. These are going to be red here. And we have these ones as red too. And then also this one, I've missed one. Okay, so all of those are going to be your gas. So where do we go from this one? Xenon is the gas of choice because it's right above neodymium, and it's going to be 6s2 4f3. So that's how to go through all of these individual examples. So whether it's an f orbital, s orbital, p orbital, d orbital, hopefully this video helped you be able to see electron configuration. Remember, it's an organization tool. It's an exact same pattern every single time. I hope that this helped. And if this method didn't, try looking up the diagonal method on YouTube. There's a lot of really good resources out there for that method as well. I will have future videos in the future. I might have one eventually later in this semester or future semesters on the diagonal method as well. I hope to see you all later. And this has been Dr. Dan. And please hit that like and subscribe button to help support the channel. It's been growing a lot. And I hope to see you back for future videos. All right, I'll see you all later now. Bye now.